Okay guys, stat 1150, following up from the first video where we looked at percentage of sea fans that were infected by the disease. That was a percentage problem. What I want to do now is I want to shift gears and look at a confidence interval problem for mean. So guys, one of the first things you got to do when you're doing your assignments and ultimately your final exam is when you read a problem that's asking for an estimation and for you to calculate a confidence interval, you have to immediately be able to determine which type of problem it is. It's very simple. When you're looking for a percentage, it's a proportion problem. When you're looking for an average, estimating an average, then you're looking at a mean problem. So guys, the overarching goal here is to take a sample mean and use it to make an inference of a population mean. And remember guys, the confidence interval formula I gave you in the previous video is to take the sample mean and add and subtract margin of error to both sides. So add margin of error to one side, the right side, subtract margin of error to get the left side. In symbols, the margin of error is the t critical times the standard error, which is s over the square root of n. Okay? Now, let's create a problem here. Let's say we would like to know, this is kind of, is actually, I saw this, I got this idea from a Gallup poll. On average, how many days per week does, well, an American bathe? Yep, kind of dorky problem, isn't it? Hopefully it's hopefully it's a number. Well, whatever. Okay, gotta watch myself. I love taking showers, so it's gonna be higher, I guess. So, what's the first thing we would do? Collect a random sample. And let's say we do that. And let's say we went out here and we sampled 35 Americans and we asked them, how many times per week do you bathe? We'll analyze the data, and let's say that we find out that the mean is 3.7 days with a standard deviation equal to 2.3 days. So guys, this is the information that we get from our sample. Okay? Now, to generalize this to all Americans, and again, this just speaks for these 35. If we went out, closed our eyes, shut our eyes for a split second, got another 35 Americans at random, we would get something different for the mean, we'd get something different for the standard deviation. Samples vary, and we have to build margin for error around our sample because there's nothing holy about it. It's good to us because it's the only one we've got. But of all the samples that could be collected from people 35 at a time, this is just one of them. So we have to build margin of error around it and create a confidence interval to generalize to all Americans. So, guys, in calculating the confidence interval, now guys, sometimes I put a little X there. That's fine. That's the same thing as S. Okay? So in calculating this confidence interval, I know that my X bar, I've got it. It's 3.7. I know over here I've got my standard deviation. That was what, 2.3? And I know that I have a sample size of 35. So the only thing I'm missing is this T star, this T critical. Now guys, remember, this T critical comes from what's called a T distribution, which is a function of degrees of freedom, which is nothing more than the sample size minus 1. So for our problem, our degrees of freedom are 34. To find this T critical for the 95% confidence interval, which we want to calculate, guys, remember, if we don't have a confidence level, always assume it's a 95. We want to look at this T distribution with degrees of freedom 34. Again, this is centered around a mean of 0. Numbers to the left are negative. Numbers to the right are positive. And we want, for this distribution, not the normal distribution. If this was a normal distribution, it'd be negative 1.96 and positive 1.96, as I showed you in the previous video. But we want it for this T distribution that has degrees of freedom 34. This is a unique distribution, different than the normal distribution. It's different than a degrees of freedom of 12 or 35 or 36. It's not going to vary much from 36. But we want it for this specific distribution that models our problem. How do we do that? Well, we're going to use Stack Crunch. Guys, it's very easy. Go to Stack, go to Calculator, but instead of stopping at normal, go on down 2 and go to T. Guys, we want between. Our degrees of freedom are 34. We want our area between the two values to be 0.95. Hit compute, and we see that our degrees of freedom, our T critical is 2.0322. Hey guys, I'm writing that. So 2.0322. So right there, 2.0322. Now, once we get this, we're going to do, just like we did in the previous video, we're going to do 3.7 minus 2.0322 times 2.3 over the square root of 35, comma 3.7 plus 2.0322 times 2.3 over the square root of 35. All right, so let's do that. I'm going to use my calculator. So I'm going to do the negative first. And then I'm going to do second function entry, and I'm going to just scroll over here and change it to a plus. So guys, I always put my smaller number first. So 2.91 up to 4.49. So interpretation, there is a 0.95 probability. This interval contains the mean number of times Americans bathe weekly, followed up with a margin of error. Guys, how do we find margin of error? What did we do in the last video? Big number, minus small number over 2. Plus or minus 0.79. Now sometimes that plus or minus isn't actually reported. I think I think on my math lab, if you include the plus or minus when it asks you to report the margin of error, it'll count it wrong. It just wants the 0.79 or however far that it tells you to round out. 2 places, 1 place, 3 place, whatever it instructs you to do. Do it. Now let's go back to this T critical a little bit. Notice the T critical changes as our sample size changes. Let's just look at some values, okay? Now guys, again, I've told you in the previous video that the 3 most commonly reported confidence intervals in research are the 90%, 95%, and 99%. The industry standard, without question, is 95%. Now, let's find the T critical for different values of n. And we're going to see that the T criticals are going to get larger as we keep our sample size consistent. And then we'll see what happens as we let our sample size get larger and larger. So I'm going to go over to StatCrunch and I'm going to fill these in very quickly. So guys, the first thing, if we have degrees of freedom 10, which meant our sample size would be 11, and I have 0.90, then I have plus or minus 1.81. 0.95, 2.23, 99, 3.17. So what I've done there is I've recorded those values. Doesn't take long with StatCrunch. Takes a lot longer than that with the graphing calculator. That's why I'm moving away from using the graphing calculator. Well, the main reason I am is because I want to try to save my students money. Let's go 25. So if we have a degrees of freedom of 25, it means our sample size is 26. 0.9 is 1.71. 95, 2.06. Guys, there's a bigger, broader issue that I'm trying to point out here. 2.79. All right, let's jump up to 50. 0.9. 1.68. Well, we will keep the 50, don't we? 0.95. 2.01. In 99. 2.68. Now, I've reported all that over here. Now, ultimately, if we get into the Z distribution, remember doing that last video? We saw that the 90 was what? 1.645. We saw 95 was 1.96, and we saw the 99 was 2.576. Notice what happens. As our sample size increases, of course, these are degrees of freedom. Actually, guys, I messed up there. This would be degrees of freedom, the way I calculated it. So sample size would be 11, sample size would be 26, and sample size would be 51. I hate that happened, but I don't think it justifies completely redoing the video, because you're expected to watch all the video anyway. So notice what happens as our sample size gets bigger. Obviously our degrees of freedom get bigger, and notice what happens to this T critical. It gets closer and closer and closer to that. If I went sample size 100, degrees of freedom 99, it would even get closer from 1.68 to 1.645. And I'll illustrate that in just a second. Closer and closer. Closer and closer and closer, right? And just for the heck of it, let's go in and look at a sample size of 200, which would be degrees of freedom 199. So guys, what was it for 0.90? 1.645. Pretty close. Let's bump it up to 299. Even closer. So guys, the point made that as our sample size gets bigger, this T distribution ultimately becomes the Z distribution. So but typically, you know, in these mean problems, we work with smaller samples. So we'll continue to use the T distribution. All right, guys, next video is going to be kind of cool, because what I'm going to show you how to do is I'm going to show you how when you're working these types of problems, you really don't even need to use that big old fancy formula. Everything that you need is provided on StackCrunch.